Hello, my name is Rahul Valappile, and today I'm going to talk to you about my oral exam. The first scenario that they put us is about a diagram to turn up a LED. First, we need to talk about the indication that it told us that the red LEDs, for example, have an operating voltage range that goes from 1.8 volts to 2.4 volts. Also, the LEDs can withstand up to 120 milliamperes without being damaged. Also, the battery whose voltage is equal to 8.7. So what I did to get the value of R1 is the next. I use the Ohm's law as a basis to make my equations, which states that to get the voltage or resistance or current, all these are related. In this case, first, I did analysis that to get the voltage that is going to V1 to L1, I subtracted 8.7 minus 2.1. I used 2.1 because of the average between 1.8 and 2.4 volts. Then this value gave me 6.6 volts that is going to V1 to L1, but also by applying the resistance. Then, to get the value of the resistor in R1 is also using the Ohm's law that I use V equals current times the resistance. So it's 6.6 equal 0.02 that I passed 120 milliamps to amps, and this times to the resistance. So we do the calculations and we have as the resistance in R1 that is 330 ohms. Then if they told us that there are only two values of resistors for R2, for R1 is 220 and 100 resistance, first we need to know if this the volts that are going through the circuit can be good for these resistors. So we also used Ohm's law and we replaced the values. That is voltage equals 0.02, that is the current, times 220, that is the resistor that they gave us. Well, the one type of resistor that they can give us. So we have the volts, that is 4.4, and also we did for the 100 resistor, well, 100 ohms resistor, that is 0.02 times 100 equals 2 volts. But this means these values of volts give us the amount of delta that is between the circuit of volts. So we need to subtract the value of the battery minus the value of volts that goes through the voltage. So it's 8.7 minus 4.4 volts in the first case, that gave us 4.3 volts, which can be available for this value of resistor. Also for 8.7 minus 2 give us 6.7. So in either case, we can use the resistors in this circuit. So in few words, it is impossible to build this circuit. And in the second scenario, they gave us the information that is, what electrical variables must be considered to guarantee maximum energy delivered in a modern defibrillator. So I used two variables that are really important. That is the capacitor and also the resistance. We know that the resistance, if it's lower, and the lower the value of the resistor, the higher the current will be. So this will be good for having a maximum energy to use the defibrillators. So in this case, if we have a really low resistance, that is in this case, for example, 1 ohms, then the current will be really, really high. Also, if we have a capacitor that is really big, then we will have a really good amount of energy that can be stored inside the defibrillator. So this will be also good to provide the maximum energy in the defibrillator. Also, in the second question, they give us what is needed to guarantee that a modern defibrillator charges in 10 seconds at most. So I use the principle of time constant to solve this problem. that is tau equals resistance times the capacitor. In this case, if we know tau is equals to, if we multiply 5 times tau, we'll get the 99.9%. That this means that the capacitor will be charged to the 99.99%. So what I did is, if we use certain values about resistance and capacitor, then we can get a value and play with it to know the best value to get it that time under 10. For example, if we use a really low resistance and a really high value of capacitor, then we will, excuse me, instead of capacitor is capacitance. So if we use a really high value of capacitance, then we will try to get a value of tau that is less than 10 seconds. Then by playing like that, we will get a really good value of tau. That means that will be less than 10 seconds. Also, in the number 3, as I said before, to how can we obtain the maximum current that is delivered to the heart during a heart rate reactivation? Well, it's really easy. So if we use the resistance that is really low, then this will help to have a really high current through the diagram or the circuit. And also to get a really maximum current, we would use a really high capacitor to provide the maximum voltage, and also by that we could get a really high current. And using the information to determine the power that a modern defibrillator dissipates in each shock, using the minimum energy in the range. This one, I use a formula that is about power. We know that first they told us modern defibrillators can now deliver from 150 joules up to 360 joules per 20 milliseconds discharge, which means that power is also 150 joules. So I just substituted in to get the power is work, that is 150 joules, because they tell us the minimum energy, divided by time, which is 0.02, because we have 20 milliseconds and I passed it to seconds. So the power that would be using the minimum is 7,500 joules in a single discharge. And based on my answers in the previous question, 2 factors that can prevent the heart from receiving enough current would be exactly the not having the enough time to provide it to charge. So if we don't have a 99.99 charge in the defibrillator, then we wouldn't get the enough power to transmit it. And also we would need enough a resistance. Also the resistance, it's really important, that if we have a really high resistance, then there wouldn't be enough current to pass through the defibrillator. So this wouldn't help to make the defibrillator or the reactivation of the heart rate. And that it is, and thank you.